some little bites. The actual lunch is going to be in the next break. It's going to be a late lunch, I must say. But I hope you're here used to that, to late lunches. Next up is a very interesting panel. I'd like to ask Paddy to come up on stage. Paddy, we have a small debate going on because his real name...
You owe me your Twitter handle.
Yeah, his real name is Patrick, of course. My name is also Patrick, but I'm the only real Patrick. I
think we should have a vote. If he should sell me his Twitter handle, that's Patrick, raise your hand. Thank you. I got some. Most people agreed with you.
I can make you an offer. It's two BTC.
2 BTC.
2 BTC. You can buy my Twitter handle today, but it's only for today.
I can give you a Paddy coin.
No Paddy coin.
And I'll use the Twitter handle to sponsor Paddy coin as well.
Okay. Well, if you buy at Patrick, then you probably increase the total market cap of your Paddy coin by tenfold.
Exactly.
So
and we'll both profit.
It will be a great investment. Anyway, you're moderating the next the next panel, and if you can introduce your guests,
of course,
then that would be amazing.
Yeah, so come on up. So
first of all, introduce yourself.
Okay, so my name's Patrick McCrory. I'm a postdoc at UCL, and I did my PhD in cryptocurrencies. So I've been doing this for 4 years now, and I mostly look at like system security and cryptography.
You're the first
in the
PhD
UK. In the UK,
right?
yeah. Yeah, so I'm the first one to graduate in the UK from it, which is awesome. So actually, when I first started my PhD, I was warned not to do it because back in 2013, as you most people here know, Bitcoin wasn't very popular. It was like $10, $1, and if Bitcoin failed, so would my PhD. So sort of like a risky topic as well. But I didn't really care. I was just sitting on like the chat rooms on Bitcoin Dev and Bitcoin Wizards, just talking about Bitcoin all day. So that entertained me, and thankfully it worked out a little bit. Yeah.
Okay.
So I guess the panelists should just come up. I'll let you guys come up first. So, and then I'll let you guys introduce yourselves as well. So I think you'll do a better job than me. So, Tim, you can go first, I guess.
Okay, let the others first.
Yeah.
So yeah, my name is Tim Ruffing. I'm from Germany. I'm a PhD student there, close to finishing, but still doing PhD there. I do cryptography, applied cryptography, and yeah, I was in the same situation when I started my PhD. Cryptocurrency was not really a thing, but I took this as a topic, and it turned out to be a very good decision. So yeah, I mostly worked on anonymity and in cryptocurrencies.
Yeah, we'll get into that in a second. All your lovely research interests. So, Ido, you should go next as well.
Okay, I'm Ido. I'm now postdoc at Cornell University in the US and did a PhD also on Bitcoin-related thesis and also some secure computation and traditional cryptography. So that was my PhD in Technion University in Israel. Yeah.
Hello, I'm Emin Günserer. I'm a professor at Cornell University and co-director of the Institute for Cryptocurrencies and Smart Contracts. I've been working on peer-to-peer systems for a long time now, about 18 years as of 2018. And I had the distinction of building one of the first cryptocurrencies back in 2001, 2002 with Karma, one of the first decentralized cryptocurrencies. So with a proof of work, by the way, that preceded Bitcoin. And I've worked on various aspects of Bitcoin, including security, scaling, and so forth, and very happy to chat about ongoing work.
My name is Eli Ben Sasson. I'm a professor of computer science at Technion. I was also Ido's advisor. I've been researching things related to proofs for the past 15 years or so, and at some point discovered that this work that was at first very theoretical actually has some applications to things like cryptocurrencies. So I'll tell you about this later, but that led to my being also one of the founding scientists of Zcash that Jack described earlier. And most recently, I'm also starting a new startup to commercialize some new technology that I'll also tell you about in the next in my talk.
Okay, that's awesome. So thank you very much for your wonderful introductions. That's much better than what I could have done. So I guess that this next question is mostly focused for Gun and how do you pronounce Ilya. Ilya. I keep getting confused with Ali. Ilya. So it's more to do with funding. So what's the funding landscape like for academics trying to do cryptocurrency research? I mean, is there any difference between now and 3 years ago? And maybe what the future would be like as well.
So I can speak to the American funding landscape. So the American funding landscape in general is actually incredibly competitive. So you have to write at least a few grants, at least 3 or so, to have a chance of being funded. So the funding rates is about 30% for most people. In some areas at certain phases in the last 5 years or so, it's been as low as 8% or 10%. So funding was normally in short supply. But there are a couple of trends that are incredibly good. One of the first things that we did was we were the first people to get funded by the NSF, the National Science Foundation in the US, and that paved the way for legitimizing the area among scientists. And so these days, the area is seen as a legitimate area of inquiry. So there are no sort of fundamental impediments. It's still a competitive area. It still takes a lot of effort to raise funding from the government. On the other hand, there's a lot of interest in industry or from industry, as you all know. And we've been quite lucky at IC3, this initiative that I mentioned, the Initiative for Cryptocurrencies and Smart Contracts, in partnering with various different companies that actually wanted to have a say and a play in cryptocurrencies as well as blockchain technologies. So we've been quite well funded as a result. So I would say overall it's actually a fantastic field at the moment in terms of funding.
Yeah, I agree with that. I just add that one trend that's now starting seems to be that cryptocurrencies that have, done various things like ICOs or pre-mining are actually starting to give back to the research community in various ways, donations and other things, and that's really tremendous.
Yeah, so my next question, I guess, is to do with really the impact of academic research. So is there any companies or anonymous individuals who are building upon your research? And more importantly, are they doing it well and right as well? And I'll start with Tim with this one. So Tim has some funny stories around this.
Yeah, I guess there are a few stories. So one nice example I think that you refer to is one of my one of the things that I did as a researcher was, as I said, I worked on anonymity, and we had this protocol called CoinShuffle. Maybe you heard of that. It's a way to mix Bitcoin, so you could potentially use it on Bitcoin itself, and it gives you some level of anonymity. And but we haven't implemented that. But people in practice try to implement that, and it's pretty sad because they don't know the crypto details. Of course, there's our academic paper. Yeah. They can read it, but I'm not sure how accessible it is. And in the end, they tried to implement that, and I think there were a few attempts, but all of them basically failed tremendously in a sense that they all got it wrong, like really at the very basic level.
I remember you mentioned you broke it in 30 minutes.
Yeah, okay, there was one implementation that recently came up, and I looked at it, and it took me like about 30 minutes to find several critical flaws in it. And of course, I knew where to look, where the critical pieces are. But I think it's a real problem, right?
No, it is. Yeah.
If we don't implement the things, and if we as academics tell people, okay, don't implement crypto, but we don't do it, then who should do it in the end?
Yeah. So I'll move on.
That's a real question.
Yeah, I'll move on to Ido now. So Ido's been advising some companies with his work.
Yes, so one experience that I have with this is I have a project about poker that can actually works very well on the Ethereum when smart contract paradigm. So there was an ICO to do poker, but when we looked at what they are doing, it was very naive. They are not really harnessing the power that Ethereum can give them. It's more like there is some trusted party, or need to have some trust that you can get rid of and do like a completely trust-free poker. So we joined their team, and we're now steering them in the right direction to implement the poker the way that it should be. Yeah, so I think like the original question, like nobody's actually taken an academic research work that I did and just implementing that without interacting with me in a good way. That doesn't happen.
So the interaction is very important then, in a sense. I mean,
Yeah.
without interacting with Tim, he broke the protocol very quickly, and by interacting with you, it's actually helping them build it.
Yeah, so in my case, it's not like in a Team's case where there is like a implementation error. It's just the design itself is not good.
Yeah,
so,
yeah, it's the implementation. Yeah, bug, yeah.
Yeah, so you need to steer them to do the correct
Yeah.
design.
I'll move on to Goon then. You have several projects, so I'll let you pick one.
So I want to actually provide some perspective on this because the situation in cryptocurrencies is fantastic. In blockchain technologies, it's amazing compared to any other field. Let me give you some examples. In the mid-1990s, I used to work on operating systems. In that field, you do some work, and you sort of put it out there as an academic publication, and you have to then wait at least a decade for the next shrink-wrapped OS release to integrate your ideas. The work I did on the Spin operating system in the mid-90s is only now finding its way into actual commercial products. So it takes a long time in just about every field. In compilers, it takes a long time. There are only a few people who actually build brand new compilers, and the release cycles are very slow. In graphics, et cetera, you have to wait for the next movie and so forth. The delay in almost every field is incredibly long. And that's in stark contrast with this particular field. This is incredibly hot. You've got these hacker kids reading the papers as soon as they come out. And much of our work has been taken on by people who want to incorporate it. Waves, for example, has incorporated the Bitcoin NG idea that my group built. I mean, I can just go on and on and on. But the bottom line is, in a hot area like this, of course you're going to have people who are eager to take the ideas, and that's wonderful. Of course there will be mistakes, because all of software is broken. It doesn't take all that much. I mean, this is one of the secrets of being a security researcher. The bugs and flaws come from an infinite source. There are infinitely many of them. And of course they'll be broken. That's okay. As long as you have a healthy attitude towards broken software, that you can fix it, you're not really wedded to your old mistakes and past mistakes. You're not in some ossified mindset where you cannot change old code. You're going to be okay. So in general, I find the field to be quite good for this. And at IC3, we've seen a lot of our software either in production or slated to go into production, because we work very closely with the companies that partner with us.
Yeah, what about you, Eli?
So my experience was a little bit different in that the handing off of the technology is a little bit more time-consuming and complicated, maybe because of the nature of the kind of code base is a little harder to grasp and work with. So I have a question. How many here, raise your hand, have tried to compile things like libsnark or write a gadget or something? Okay.
Ooh,
wow. Actually, I'm impressed.
I'm really
I am
impressed.
very impressed. Okay, wow. Like there were I think 7 to 10 hands, but it's not that easy to use. So my own experience was this. I always describe it as this bittersweet story where at first you're really needed and your advice is sought. I mean, this is the experience with Zcash, and as time goes on, you sort of you make a comment and you see that it's politely ignored, and at some point you realize that enough knowledge has been transferred on to the new set of experts, and that's the way it works. Yeah. So,
although you also have a new project now. It's really hard to pronounce. Zocrates. Have you heard of it? Where it's like
Zocrates. I thought.
Is that how you pronounce it? Zocrates.
I thought it's like Socrates, no?
Socrates.
Socrates.
I was going with the Miller punctuation. Socrates. Anyway, so what do you think about those type of approaches as well, where they're trying to do it so you can write in a high-level language to compile down the snarks? I mean, that's a huge improvement, isn't it?
Great, yeah. I mean, well, the original paper that released the libsnark was called Snarks for C. So there was some rudimentary compiler there, but it's really great that there are, higher grade ones being worked on.
It was presented at DevCon. I thought it was really exciting,
Yeah.
Okay, I'll move on to my next question. So this sort of builds on what you guys were talking about. So academic papers are really hard to read. So, so how do you make them accessible to the developers and the wider community? I mean, is there when you're talking to developers, do you find there's a language barrier where they read the paper and they just don't fully grasp it? I can go with. I'll go.
I'll go first because my experience of recent has been the other way around. That the developers like jump on the papers, and it's actually more the academic community that sort of, you know, we don't know about this. So, well, you know, I can't read code, for instance. It's very complicated. But if you, you know, put enough time into it and dig deep enough into it and study it, and slowly some mental picture of what's going on emerges. And I think this is with all kind of, you know.
Yeah, I think the learning curve, isn't it? I mean, it starts very slow, and then it like becomes exponential.
Yeah, I often have this image of like these, you know, there are these pictures where 3D things where you stare at and you see nothing, and then suddenly something pops up. So it's the same sort of thing, I think, with let's say mathematical or abstract research, that you stare at something for a long while, and then suddenly one day you wake up in the morning and you say, oh, you know, I understand it, or I see something.
So yeah, so as I mentioned before, I think we're living through an interesting time. This whole hyper-tokenization effort, the ICO craze, has created a large group of people who love to read research hot off the press. And so we find that anything that we do, even things that we didn't mean to put on the web but somehow ended up on the web, is scrutinized heavily by people. This is a wonderful outcome. And but you know, Patty is asking this question of what is it that we have to do to be more accessible. I find that you know, the time I spend reaching out to you know, regular people who are not technical people is very, very well spent, because the spending decisions, the money decisions, have to be made by people who actually understand the technology. I would like them to fund blockchains, or as they call it, blockchain, and without an article, by the way, just like the word God. It's not a blockchain or the blockchain, it's just blockchain. And so I would like them to fund the area, not because of the hype, but because they understand it. And so the bridges we build to them are invaluable. The other thing that I do is I spend a bunch of time working on a blog to try to make the ideas accessible without equations, without complicated protocol definitions. So the blog that I run is called Hacking Distributed. It's a shared blog. Lots of people, lots of academics post there. And it tries to make some of the sort of the hot off the press ideas accessible to the general audience. And we've found that that's been a great way to reach out.
Yeah, I think I certainly agree. This is what you said, right? In all, like cryptocurrencies is or blockchain is a very special field for us, because usually when you write a paper, you hope that in 10 years somebody could use it, and in cryptocurrencies, people will implement it before you actually have the paper out. This is what you said, and I think this is actually a good thing, and it's special for us because it takes more time, but we really should invest this time, even though it doesn't give us more publications, but it moves the entire public forward, right? And also, it's like as a researcher, it's great if you see that people are interested, really like developers interested in your stuff and want to use it in the real world. I think even seeing that is a nice experience. So we should really invest this time and be available for people, and talk to developers, talk to implementers, talk to business people.
So about how to make the academic paper accessible. So yeah, I guess I try to write an overview section before the formal section and give examples, but usually it's still difficult because like the paper needs to specify all the details and it becomes overwhelming. So also try just to put the presentation on my homepage. Yeah.
Yeah. But
So I was going to also point out one big tension for any academic. So when you're writing the paper, you're writing for your colleagues who are going to nitpick it to death, and every definition has to be incredibly well done, and so on and so forth. So there is that on one side, that tension. And when you want to reach the normal people, you want to just talk a little loosely. You know, roughly speaking, here is the problem that we're trying to face. And if you write that in a paper, that's an instant reject, right? So the paper is not really allowed to have that language. So that creates some tension. And but then there are weird dynamics that develop, and I want to caution you all to this. So then developers can start nitpicking the accessible text that you wrote. And this I find very, very annoying. So when I write something, like, roughly speaking, this is what we want to do. The worst thing that anybody can do, the sign of a small mind, of somebody that I really don't want to deal with, somebody who says, well, in this blog post on line 3, you said da 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 da. Well, the whole point of the blog post was to actually try to make it accessible. This is where we take some liberties with the specification. If you want the full spec, it's in the paper. So mixing those worlds and mixing those modes of interaction is a big no-no. So you should all know this when interacting with academics, because it's the papers that are bulletproof and specific and precise, and the other stuff is the accessible stuff is going to try to be accessible. And if you try to mix the modes of interaction, you're being an idiot. It's for a specific person in the audience.
Yeah. So I'm going to move the discussion on a little bit more. So I've had this myself a few times. So there's a bit of truth to this question in terms of people's perception. So there is a perception that academic work is disconnected from reality. And I've had that so many times. I've said in a meeting that they're like, oh, but you're an academic. That's like an academic dream. I'm like, I'm an engineer who writes papers. So yeah, anyway, so I'd like to get your comments. So I'll go with Tim first, I guess, since you're the closest.
Yeah, I think there's some truth to it, actually. Yeah. If you look at the entire field of cryptocurrency, starting with Bitcoin, I mean, it started not as an academic thing, and it took us years in academia to convince other researchers that it actually has some value, and now it's suddenly a hot topic, and now we suddenly realized, okay, this is a real thing, and it solves a fundamental problem that we didn't know how to solve earlier, and I think this started a nice trend, and I think communities are converging to each other, but there's still more work to do.
No, I think so. Like, even when I started my PhD back in 2013, there's probably only like about 10 papers, 5 papers, and Bitcoin being around for 4 years. So there's no interest. I'm sure Gun mentioned your paper was like the 13th or something. Yeah. You can continue now, Gun, I guess, since we're quite,
Yeah, I guess some of this is true. So I guess like now there are these trends in academic theoretical crypto about obfuscated circuits or whatever that is very far from reality, and they're still keep researching these very tiny delta improvements and that kind of a thing. So yeah, some of the academic research might not be so useful. Some of it's very, like public key cryptography. It started as academic RSA and so on. Yeah.
So yeah, I think that's what you're going to get from almost every academic. We all realize that academic work is academic. And, we explore ideas because of what they might lead to, not necessarily because they're immediately useful right now, right? This is not carpentry. This is cryptography. So you might not be able to create, something immediately with it, but there is often not often, there's some probability that there's something of value that lies at the end of this line of inquiry. And so it's crucial to be open-minded about where work might lead to. It's crucial to fill in the gaps, and there are oftentimes where components are used as a black box. There are oftentimes assumptions made that certain things can and will happen in the future, and that's okay. It's the right thing to do is to be open-minded about these things and to allow people to say, okay, well, let's assume the presence of such and such an entity. We all understand that entity doesn't exist. We all understand we don't know how to build it yet, and yet, nevertheless, we're going to take that as a given and build something on top. And so this is an important way to make progress. And so, yes, on the other hand, is it not true that a lot of academic work is disconnected or makes a simplifying assumption that is not true in the real world? And in fact, isn't it true that much academic work makes assumptions that will never be true in the real world? Those are all true as well. And that doesn't bother me, and I don't think it should bother anybody. That it's okay to have somebody inquire down a path that may or may not be useful down the line. And people are judged here by their ability to have impact at the end of the day. It's those papers that actually are valid in the real world that end up being cited, that end up being elevated. So that's the system kind of works, roughly speaking, and it's the best system we know to build. There is none other that I know of.
I think academics are deep space explorers, venturing into the unknown. But the space we are exploring is the space of possibilities in human knowledge. And there's a lot of risk involved, not physical risk, but risk of making a lot of mistakes, of going into paths that later on you understand led to nowhere, just like when you're exploring some unknown territory. But it's very important that society have these explorers, because sometimes you stumble upon something of great value. So the nature of academic work is this very abstract exploration just on the boundary of what's known. This is very opposed to what businesses strive to do, which is to, try to improve things by the smallest amount of effort, make the biggest improvement. And academics are the opposite. They try to put in effort into going to things that are just barely or not even clear if they're possible. That's what we do. So, but you need both.
Okay, so I'm going to close now. So the question's to do with, can you sum up the future relationship between academia, researchers, and the wider blockchain community? And this is sort of in the backdrop of these sort of, $300 million funded startups, the government grants, et cetera, and the different forms of discussion. How do you think the relationship's going to evolve? I'll let everyone take a short note on this.
I want to start. So decentralized cryptocurrencies could work very well with this decentralized society called science. And we're starting to see this. So it would be really, really great if we see more of this. Who knows, maybe someday scientists will compete for consensus, which is what we all compete about, reaching it on some sort of blockchain. But in the meantime, cryptocurrencies, please keep up the funding and the support. That's really great.
And really needed.
Yeah, I think the system is self-correcting. We're as I mentioned, living in a very, very interesting time. There are lots of projects that are very well funded, and I would say overfunded. As Ellie mentioned, they are thinking about giving back to the community. They understand that they perhaps got lucky, and so on and so forth, and that they I think maybe the key thing to realize is that it takes an ecosystem to make progress in any given direction. And that ecosystem has to have business people in it, has to have scientists in it, has to have implementers in it, and a variety of people who've built services on top in it. So fostering that community is crucial. And there was a previous discussion in the hallway before about what gives value to cryptocurrencies. Why should X be worth more than Y? And it's not because of limited supply, right? So imagine that if we reduced all science, the number of scientists working on a problem, it wouldn't go up in value, right? You can see this. Similarly, 21 million Bitcoin doesn't make Bitcoin valuable. What makes it valuable is the community built around any currency. And similarly, the communities built around ideas are what's crucial. So to the extent that we can foster a working, functioning, positive, healthy group, then we will have succeeded.
Can you now ask questions?
Oh, yeah. Should we have a Q&A? Like a few, like 2 or 3.
We can, but we're running like 15 minutes late.
Okay, can I take 2 questions? Okay.
But maybe a better idea is if you have a question, just to come over here and ask the question behind the scenes. Yeah, is that okay?
Okay, then 2 more sums up, and then we're done.
So about your question, yeah, I don't have much useful to add. I just remember that there were some complaints from several years ago, let's say from the Bitcoin developers, that what is actually being done in the development community, the academic people don't look carefully, and then they either replicate or do something that didn't take into account. So it also goes the other way, that the academic community should try to look at the development community and see what they're doing.
I think as Ellie mentioned, we have these 2 communities, and they both make sense, right? And they both should continue to exist, of course, and work in their in their own community. But we should talk to each other. This is the thing we need to do, I guess, and then we will understand each other better.
Okay, thank you guys for answering all these questions. If you want to talk to any of the speakers, we can find them afterwards. Can we give them a little round of applause to say thank you for their hard work? Thank you. Okay. Awesome.
So, Tim, you're actually Well, can you use this or? Yeah, perfect. Thank you. Also, next up is Tim. He's going to talk about A Tale of Zero Coins, and he's going to use the handheld mic. In the meantime, I'll get rid of this, but you can already start because we're running a bit late.
You press F, then we got full screen even. Yeah. Yeah, great. Okay, so this is, as you said, this is A Tale of Zero Coins, and at the moment this title doesn't say a lot, but I hope you will understand it during the talk. This is joint work with colleagues from Germany. So as I mentioned earlier, I'm at Saarland University in Germany, and my colleagues Aravind, Victoria, and Dominic are at Friedrich Alexander University in Nuremberg. And if you want to follow me on Twitter, this is my handle. Okay. This is actually a talk about another. This is work done by us, but it relates to some other project, and it's about Zerocoin. Zerocoin is a paper by those people: Ian Myers, Christina German, Matthew Green, Aviel D. Robin, and it's about anonymous cryptocurrencies. So it's a design for anonymous cryptocurrency, basically. And actually, there is another paper that builds on the same model, and I should have mentioned that here because one of the authors of the other papers is in the audience. So sorry for not mentioning you. There's another paper by Jens Groth and Markov Kovács who build on the same model. And actually, this talk applies to that as well, but I didn't mention it on the slides. So this paper here has appeared at IEEE Security and Privacy, which is kind of the largest or the most prestigious conference in security. And the idea is, so this is proposed as an extension to Bitcoin or similar cryptocurrencies, and it works like as a cryptographic mixer to improve anonymity. So we will see in a minute what it means. And interesting here, so this is an academic work, so it comes with a detailed security model, a formal security model, and a formal security proof. And actually, people picked this up and implemented it. So, and there are a few cryptocurrencies who really implemented it. So there's Zcoin, Pivx, Smartcash, Zoin, and Hex, and maybe there are more. Those are the ones I found. And they use an implementation of Zerocoin. And I looked at the market cap. So these are not like super large cryptocurrencies, but there is some money involved. At least if you look at the figures from 2 days ago, I mean, it could be totally different now. I have no idea what's going on, but 2 days ago, there was some money involved. So in just a small disclaimer, so don't get this wrong. This is about Zerocoin. All of this talk is about Zerocoin. It's not about Zerocash or Zcash, which is an implementation of Zerocash. So you can consider Zerocoin a predecessor of Zerocash. You don't have to, but this is about Zerocoin and not Zerocash. Okay, so how does it work? So the idea is that there are two basic operations. The first operation is, so given one regular coin, say I mentioned that this has been implemented in Zcoin, for example. So given one Zcoin, you're allowed to exchange this coin in a Zerocoin. This is called mint. So basically, you give up your regular coin, and what you get back is you get back a Zerocoin. And there's a second operation that does kind of the opposite. So given such a minted Zerocoin, you can convert it back to a regular coin. This is called spend. Okay, so far this seems boring. So you can convert a coin into a Zerocoin, you can convert it back, so what's the point? Actually, the idea is that during the spend operation, you get some form of anonymity because you use the zero knowledge proof, and instead of telling the world which Zerocoin you're actually spending and giving to someone else, you create a zero knowledge proof, and the proof just reveals that you are eligible to spend one Zerocoin, but you don't reveal which one you spend. So this is where some anonymity comes. So for an observer, it basically looks like this. So like, imagine these are 4 Zerocoins on the left, and we are spending the second one, and an observer can't tell actually this apart from a scenario where we would be spending the lowest coin here. So the idea is you get anonymity by spending a zero coin, but you don't tell people which one you're spending. And this is done in zero knowledge, and it doesn't matter how it actually works. So the problem with this model is, of course, we don't want to allow double spending, right? You shouldn't. If you have one zero coin, you should be able to spend it only once. And the problem is, so if I don't tell you which coin I'm spending, how should you, as a verifier, check that I'm not spending the same coin twice? And the idea to solve that, and which is used in zero coins, actually pretty simple. So each zero coin has a random, what is called serial number. And when you're spending it, you reveal the serial number. And it's unique to the coin. And actually, you're forced to reveal the correct serial number. That doesn't break anonymity because you never revealed the serial number before. You will never reveal it in the future, so people can't relate it to anything. But if you spend the same coin twice, you would reveal the same serial number twice, so people can now notice, okay, this is actually a double spend. So, for example, if you do this spend operation, this could be a serial number, and the zero knowledge proof makes sure that you can't lie about this. So, if the serial number appears for a second time, it's invalid. So let's say we reveal this serial number, we spend another coin, reveal this serial number, we spend another coin, reveal this one, and then if you're malicious, we could try to spend the second coin again, but then we would have to reveal the same serial number again, so everybody would recognize, okay, this is double spend, it should be invalid. Okay, and in this security model, in this formal security model in the paper, there's one property that's called balance, and it basically says the attacker cannot perform more spend operations than mint operations, which intuitively makes sense because if I mint 10 coins, I shouldn't be able to spend 11, right? So because then I create money out of thin air. And actually, yeah, this property implies that no attacker can create zero coins out of thin air, so that's good. And it also implies that no attacker can steal 0 coins of honest users. That's also good. But there's a problem. So actually, something is missing there. And this is what we figured out. So the missing part is that actually this balance property doesn't prevent you from burning 0 coins of honest users. It just says, okay, you can't steal coins, but maybe you can destroy coins of honest users. Yeah. So maybe we can buy money. So I'm from Germany. I'm burning euros. So it's starting to get interesting. Okay, so the security model does not prevent the attacker from burning coins, but can we really do it? Like, so far we just seen, okay, it's not required that this should hold, but maybe we're lucky and the actual construction it doesn't allow it. But just let us look at how such an attack would look like. So say we are the attacker. The first thing we do is, we see a spend transaction from an honest user. May look like that. So an honest user is spending a coin and reveals the serial number. We see this on the network. And what we're doing, we're sitting on the network, so we just block these transactions. We don't let it through, so it will never reach the blockchain. But we learned the serial number. So now what we could try to do is we could try to mint a 0 coin that has the same serial number. This is this red coin. And the question will be if this will be possible. But if we could do so, then we could spend this 0 coin. And now it has the serial number that is the same serial number as in the honest coin. So now if the user the honest user would try to spend this yellow coin, it would be rejected as a double spend, right? Because the serial number is already revealed. So yeah, so now the user can't spend her money anymore. So and actually the question is, can the attacker really choose the serial number freely? Because this is what would make the attack work on the previous slide. And actually, yes, he can. The thing is that the output of a mint transaction, it's basically the coin itself. So it's public information, which is called the coin. And there's a corresponding private key. And the 0 coin, so this public information is a commitment to the serial number. It doesn't matter if you know what a commitment is or not, or this is actually the mint algorithm from the paper. S here is the serial number, and what happens is that in honest users are supposed to select the serial number uniformly at random. So this such that if you have two honest users, the probability that they will share the same serial number for 2 minted coins is basically nothing. But there's nothing in this mint algorithm which prevents an attacker from, instead of choosing a random serial number, just take another serial number and putting it into the mint operation. So it's actually possible. The attacker can choose the serial number freely, so the attack works. So we can actually burn money. So that's why it's a tale of 0 coins. I don't know if you get the pun. It's pretty bad. Okay. So can we do this in practice? Yeah, we could, but it's difficult. It's actually a double spending race for the attacker. Because if the attacker doesn't manage to block this honest transaction, that actually we might up reversing the attack such that the honest user's transactions go through and then blocks the transaction from the attacker. So actually if the honest user wins on the network, wins this double spending race on the network, then actually the attacker loses his money. So it may be hard to pull off in practice. However, if you like really control the network of the victim, or if you are a miner, then you have some advantage because you can hope to mine a block and then control the transactions that go through into the block. So this is really feasible. But there is no evidence that this actually has been done in practice. And so far this is only about like destroying coins. We can burn coins. So this is pretty nasty, right? But usually we don't. As an attacker, I'm not interested in destroying coins. I want to profit. So can we do this? And maybe we can. So one possibility that we could use is insider trading, in the sense that we try to short sell the currency. And I don't claim that dimensioned currencies are easy to borrow, so to do this thing. But in general, there's nothing that prevents us from shorting a currency. And then we go to the public as an attacker and say, oh, all this is broken. I can burn coins. That the thing is wrong and whatever. And when we hope that people will sell their coins and then the price drops and then we profit. So I'm not claiming that this will work necessarily, but it's a strategy. You could use it. Okay, so let's fix it. And the fix is actually super simple. And so far, serial numbers have just been random bit strings chosen by the users. And now if we, instead of using a random bit string as a serial number, we use a public key, so a new public key of a signature scheme. And we additionally, when we reveal this serial number, so the serial number is a public key now, when we reveal the serial number in a spend transaction, we additionally sign the spend transaction under this public key. And this doesn't break anonymity because this public key, it's like in the serial number, we haven't seen it before, we will never see it later. But now it prevents this attack, because if the attacker now creates a second zero coin with the same serial number, and he can still do that, then he won't be able to spend this second zero coin because he doesn't have the private key corresponding to our public key. So he can still do the first steps of the attack, he can still interrupt our spend transaction, he can still mint a zero coin with the same serial number, but he just won't be able to spend it, and this just blocks the attack. Okay, so after we found this, we contacted the original zero coin authors, and they confirmed that it's a real issue. And then we contacted the Zcoin developers. It was a little bit bad because at this time we were only aware about the Zcoin as an implementation. So we contacted them, and we told them, okay, look, there's a problem in the protocol. Can you fix this? And they said, like, I have no idea what's going on, actually. So that's why they asked me to fix it. And actually, I did it, yeah. So they hired me to implement the fix. Okay. Then I looked at the code, right? Because I was trying to implement the fix, and then I found a lot of implementation issues in the code, actually, very serious issues. I have to say here that I will come to that again, but what they basically did is they took an academic prototype. So they took the prototype of the original Zerocoin authors and just took it and used it. And this is probably not a good idea. We will see in a minute why. And so yeah, so there were very serious issues. So you could actually create coins out of thin air. This has been fixed. There are more issues, and I can't actually talk about everything because not everything has been fixed. It's still they're still working on it, and actually we will release a public statement like in a few days, but it's almost done. So okay, only later that was bad. Then we found out that there are actually more currencies than more currencies than Zcoin who use this, and some of them, yeah, we couldn't know for all of them because some of them were just really in development when we found this. Finally, we contacted all of them and helped them to integrate the fixes. And yeah, a lot of hard forks happened, soft forks happened, and as I said, more forks are required. Yeah, and we will release a public statement in a couple of days. So yeah, and then, because then we found these other 4 currencies, we asked ourselves, so are these really all currencies? Can we be sure? And then, yeah, we think so, but it's super hard to keep an overview because then what can you do, right? We went to GitHub and did a code search just to check, oh, has anybody used this library? And this is what you get, like you get like 1,693 repositories who included this libZeroCoin, which was the academic prototype implementation. And when I saw this, like, what the fuck? What are all these things? And if you look closer, this is actually a search for a very specific code pattern. And it turns out that there are really like over 1,600 repositories on GitHub who have, which have this library in their repository, but they don't use it. If you have a closer look here, it just says if 0. So for some reasons, there's some guy who copied like this library a lot of times into some repositories, and yeah, they don't use it. I have no idea why. Yeah, one thing we found that could be related to this, but we can't prove it, is there was some cryptocurrency generator in a sense. Or I don't know if it's an automated generator, but there was a website. It's down now, but it's archived. And there was a website where you could buy your coin. You could buy an ICO, including a website, including code. Yeah, they say you get the compiled Linux and Windows client, currency name, everything, and you can get this for $550. You see, it's an offer. You should be quick. I think you get a. I'm not sure if you get a white paper. Yeah, but there are also projects where you can get white papers here. And we think this is related because here they mentioned this Regal coin, and Regal coin was one of the currencies that we found on GitHub that exactly had this code pattern. But it's like just a connection. I can't be sure, but probably this is where all the weird currencies come from. And they don't seem to be used in praxis, but yeah, who knows? Okay, so yeah, some lessons learned. Nothing surprising. So provable security is not a silver bullet. Okay, we talked about this relation between academic and academic community and implementation. And even if there is a formal security model and a formal security proof, that's super great, but we have to be careful what the model actually is. Because if we miss some properties, the best proof won't help us. Yeah. Of course, yeah, also not news, don't implement crypto that you don't understand. And don't use academic prototype implementations that come with big fat warnings. Because I can't blame the Zerocoin authors for this. Because like, these were the warnings, okay? So it's pretty obvious in the README file. So if you ignore these 3 warnings, then yeah, nobody can help you, right? But if you really want to use such a library, then please go ahead and at least remove the warnings, right? It's still, if you look at the Zcoin repo today, it's still in there, in the subfolder of the library. So the warning is still alive. Yeah, so there's a lot of weird things going on in the space, and there actually was examples. So this is actually a good thing because they took an academic proposal with a proof and so on. So I think that's good. And I think the problem is there are only a few dozen people in the world who are able to maintain a currency. But if you look at CoinMarketCap, there are like 1,500 currencies. So that's an obvious problem. And we need more education and be careful with your money. Yeah, thanks.
Thank you. Oh. He just said, be careful with your money, but you also need to be careful for the steps. Yeah. And next up is a familiar face who also joined the panel. Haley, come up and share us with your knowledge.
Okay. Hello. So I'm going to talk to you. I'm going to speak today about, about scalability, transparency, and privacy using crypto proofs for cryptocurrencies. Okay. And, okay, so a brief introduction. Money used to be limited physical resources like gold. And then we moved on to fiat money, which is made limited by decision, usually of some central party, like a bank. And now we have cryptocurrencies where the limitation is by consensus of a large, decentralized, permissionless network. And that's really impressive and amazing. And when people ask me what's the main thing or the ingenious part of, or the main innovation in Bitcoin, there could be many answers. This is mine. It's the first time some societal function, something that a large society needs, which we thought requires a trusted party to manage, has been replaced by some ingenious mix of economic incentives and protocols and computers. And in the case of Bitcoin, this was money. But there are other societal functions that we all need and right now are managed by various central entities like law, corporations, government, academia, religion. And you could ask, what next? And this is a very interesting question. Now, when you replace the trusted party model that everyone trusts with something decentralized, then you start facing new problems. And one important one, if you use computers, is that of computational integrity. So what is it? It's a very simple to state problem. How do you know that when someone tells you the output of the computer is the number 7, how do you know that he is not lying? And of course, in systems like Bitcoin, this could be of tremendous economic value and consequence. So the point is that often, and we know this in the context of cryptocurrencies, the parties running the code have incentives, economic incentives, big ones. I think the cryptocurrency market today is around $500 billion. So that's a lot of money. And you are incentivized to misreport the output, and that's a big problem. It's not such a big problem when you're just a small party in a bigger system, because then there are more checks and balances in place. But the problem gets bigger and bigger as the party running the computation gets bigger and more powerful, to the extreme when governments run computations, well, and they say, the output is something, it's a big question. Can we trust them? Do we have ways of enforcing and making sure in a transparent and efficient way that they're saying the truth? So Bitcoin's solution is known to all of us. It's everyone sees everything and then recomputes and validates everything out there. And this works very well. But it raises two problems. One is privacy, right? All transactions are there for everyone to see. And the second one is scalability, because now everyone has to repeat a lot of work because you can't trust anyone else. And I'd like to address these two things. So let's rephrase the question. How can we have this big system where the public gets to trust the output of a computation and yet have these computations be scalable, deal with larger and larger payloads without stopping or coming to a halt, as we see today with the case of CryptoKitties in Ethereum, or the transaction per second of Bitcoin, TPS, which is around 10, whereas Visa has around 2,000 per second, and things like Alipay have 250,000 transactions per second. So how do we reach that goal? And how do we do this while preserving privacy? And one answer, the one that my colleagues and collaborators and myself have been exploring, is to use things called, informally, cryptographic proofs. So they were invented about 30 years ago. And they're very famous among computer science circles. And I think now they're starting to become a little bit more general public information. And for a long while, they've been only discussed theoretically or academically. But now they're starting to be realized in code and used in systems and products. So I want to explain what is a zero-knowledge cryptographic proof. This is how I explain it, let's say, to my mother. So it's a little bit like a grocery receipt or a restaurant bill. It's a string of data that enforces and makes sure that the person generating this thing is actually saying the truth. In the case of a restaurant bill, that is that the person is convincing you to pay the total sum. And the reason this is convincing is that you can re-execute the same computation of summing up the items. And we used to do this back in the day where we got written things. Maybe we should still be doing this, just in case there's some glitch or someone is cheating us. So we have here a naive proof by re-execution. So again, we have a proof. The proof is this string of characters, and it's convincing. It does enforce computational integrity. So zero-knowledge or cryptographic proofs are a little bit the same, but there are some subtle differences. So the first thing is this privacy-preserving aspect, which is suppose that like all items are blanked out, and the only thing that appears in the end is the total sum is $21. This is one aspect of zero-knowledge proofs, right? That they could blank out all the auxiliary inputs that go into a computation, things like private keys, passwords, medical information. Another interesting aspect is that you could apply or get a proof not just for summing up numbers, but for any computation. Something, I scanned the database and I checked some things and the answer is 7. You can still have a proof for that. And the last thing is scalability. So suppose if you ran the computer program naively and you trusted, or it is being executed by someone you trust, suppose this computation takes T steps. So now you're in the untrusted world and you would like to verify or generate these proofs. So you can verify scalably, meaning you get exponential savings in verification time. So as T goes to infinity, the time needed to verify one of these proofs doesn't go like T. It grows like logarithm of T. So there's an exponential compression in running time, which could be very useful in the context of, let's say, blockchains. Maybe one node could say, I processed 1 million transactions, and here's an update to the state of the system. And then everyone else doesn't have to do 1 million steps of computation. They could just do it with logarithm of 1 million, which is around 20. And the other thing, which is also very important, is that generating these proofs that go along with the scalable verification are also scalable, meaning that to generate the proof is not too much longer than just performing the computation naively. And specifically, it's called quasi-linear running time. So I just gave some numbers here. Let's go to the last one. Suppose the computation T would have taken a peta number of steps, which is roughly 2 to the power 50. It's a huge number. Logarithm of 2 to the 50 is only 50, and logarithm squared is only 2,500 steps, which is much, much less than a peta. It's like a kilo, 2.5 kilos. And the same thing with the running time. The running time does get a little bit larger by a factor of 2,500. That's unfortunate, but it's not too bad. OK, so this is the nature of scalability. Now, I used to do mathematics and slowly realized that this mathematics that was about getting certain kinds of proofs to be more efficient is actually relevant to, could be implemented. So we started implementing them with no good reason in mind. But then in 2013, when I was walking among academic institutions and trying to market this thing, it was very hard to explain why someone would need these proof systems. And I also ventured upon the Bitcoin San Jose conference, and there I had this sort of eureka moment, because people who are used to the trusted party model. You know, the Googles, Amazons, banks, governments of the world, when you explain to them, and that's most of us, or used to be most of us, you say, oh, I have this thing where someone can prove something to someone else. They'll say, wait, who? The bank is going to prove to you something, or you prove to the bank? What do you mean? The bank keeps all your data, and you better trust the bank, otherwise, you know, you're screwed. So they would ask, what is a zero-knowledge proof? How does it work? Like, why does someone need it? And when you talk to people from the decentralized community, they don't ask those questions. They say, OK, where's the code? You know, can we start using it? We'll give you 5 examples of where this is needed right now. And this has been the case since then. OK, so we joined forces with the Johns Hopkins team that was behind the ZeroCoin paper. And we published this academic paper, Zero Cash. It's an academic paper. There was some academic grade code, all the things Tim said about, you know, not using academic grade code in the system apply. So later on, we joined forces with a great team of engineers led by Zuko. And Jack is our CEO. He spoke earlier. And there's Zcash today. Now, so I'm one of the founding scientists, along with all my other 6 co-authors on the Zero Cash paper. And now I want to tell you about some new technology called ZK Starks. And there's also a new startup that, you know, just like we're just now, you know, how do you say, taking the wrappers off of this company called Starkware. So I'll tell you a little bit about these. OK, so first of all, how do these privacy-preserving proofs work in reality? So I'll give a very high-level overview. So in Bitcoin, when Alice pays Bob, she has sort of this random-looking key, this red thing here, and Bob has a random-looking key. And then she posts for everyone to see this transaction that says, this key transfers to this key 5.2 coins. OK. But now, when Bob is going to spend that coin, he will use the same key. And then Alice gets to know that he just spent the coins. And you can do a lot more analysis and learn more about what's going on. So the idea in Zero Cash and in Zcash in one line is to sort of take that transaction and put it inside a cryptographic envelope where no one sees what's in there, so no one knows what's going on. And then you slap on another proof on the side that proves that what is inside the envelope, even though you're not revealing it, is legitimate. Okay? And the mechanism, or the cryptographic kind of proof that we have there, is called the ZK Snark. It's very short, 300 bytes or less, very fast verification. You could apply it to any computation. But there are a few things that we wanted to improve. Like there's a requirement for a trusted setup that cannot be transparent. And if you compromise the trusted setup, then you can use whatever you reveal there to basically forge money. There's also quantum algorithms can break it, but let's not go into that. So this is, I just downloaded this today. I mean, you know, this morning. I think it's right now. I don't know what the price is right now, but this is a plot of the Zcash cryptocurrency. Yeah. So we had these problems with ZK Snarks, and now I want to tell you about some new technology that solves these 3 problems. So we call it ZK Stark. It's also work with Ido Bentov, who spoke earlier, Inon Choresh and Michael Ryabtsev. And the main things are its scalable proof generation and verification, and transparent, meaning everything involved in it is just public randomness. So I just want to say briefly that the transparency is very important, especially so in the context of a community or a cryptocurrency, for instance, like in the Zcash one, which isn't as powerful, let's say, as a central government, you could fly by and get some sort of ongoing public trust by distributing it a little bit, like the key generation protocol, which is something that's going on right now in Zcash. But if you think about governments and central entities, if you would want them to be more transparent and accountable to their statements about various secret databases that they hold, then now you really need full transparency of the kind that we achieve with Starks. It's also important if you have a collaborative creation of crypto proofs for new programs. You don't want to then worry about who's generating the keys and what's happening there. OK, so that's why I think transparency is a very important thing on its own. So here's an example of a benchmark code that we actually implemented and tested. Suppose some central entity like the FBI has a DNA profile database of all forensic DNAs picked up from crime scenes. And now there's this president-elect that the FBI is claiming that her fingerprint does not appear in that database. It's completely hypothetical, right? These things never happen in reality. Questioning the integrity of various presidential candidates. Anyways, so the FBI needs to generate a report that will convince the public that everything's okay. So basically the program would run over this private database and compute the hash of it or the commitment and also check whether there is a match. So we ran this program, and then we also wanted to test things like, does our proof really scale well, or proof methods scale well? And for that, you could sort of take the ratio of the time that it takes to verify a computation in our system versus the time that it takes to do it naively. And you could do the same thing with the size of the witness or the database. How long is the proof that we generate versus how long is the proof of the naive proof, which is just the database with all the fingerprints in it. So, and here are some measurements. The main thing is that we have realized for the first time, in this kind of system, that you can have actually meaningful compression and scalability, meaning that the verification is actually faster and shorter than doing things naively. And as you can see, the larger the computation size, the more savings you will get from this scalability. So ours is just one of many, many realized systems. I'm just flashing here, this is more for the academics. I'll just point out that Professor Jens Groth sitting here is one of the main innovators in the line that later on led to the systems behind Zcash and LibSnark. But there's a bunch of different techniques. They're all very useful. So I just want to show you some measurements and comparisons. So you could look at various properties, and I'll go over this very quickly. So ZK-STARKS is sort of all in the green, post-quantum secure, transparent, verifiable. Verifier is scalable as well as prover. And then we went and sort of measured running times of these. We tried to do an apples-to-apples comparison using the same computer system and for the same size of computation. And again, I don't want to go into detail too much on how we did this. But the green is the ZK-STARKS. It's 10 times faster in the prover than the fastest second runner-up, which is the ZK-SNARKs. There are other systems that are also almost as efficient. And here are the verifier measurements. So the verifier is not as fast as things like the ZK-SNARKs, but that's only if you take into account what's called the post-processing, the part that comes after you generated the keys. If you need to generate keys for new computations or larger ones, then actually the ZK-SNARKs are pretty long. Same thing with the size of the keys and the proofs. So, but these are some numbers that show that at least this kind of system could work well. So in closing, I just want to tell you, I have 1 minute. I just want to tell you a little bit about this new startup. So we just sort of formed. We have 10 employees. Almost all of us are engineers or scientists, including my co-founders, Alessandro Chiesa, Uri Kolodny, Michael Ryabtsev. We just closed a $6 million funding round. We're located in Israel. Our vision right now is that we believe that the kind of technologies that we have, these transparent and scalable zero-knowledge proofs, will bring value to permissionless cryptocurrencies. We're focused initially on the permissionless as opposed to the permissioned space. So I think that if we're just looking at where we are, so we have established through academic papers some sort of understanding of the science and technology. Okay? Our next focus right now is going to be on a product which is just building a really good scalability demo or solution. And later on, in terms of monetization, we would like to be able to capture a percentage of the increase in value that our systems are offering to various public cryptocurrencies out there. And if you're interested in details, you can come offline. So concluding remarks, Bitcoin's innovation is a decentralized system, no trusted party, but it raises new problems of scalability, privacy, and integrity. Crypto proofs like the one in Zcash solve the problem. And we have this new technology that we would also very much like to explore. So question one, which societal functions
will be disrupted next? This is the really big question, and one that's more interesting to us is what can these ZK Starks and Starkware do for you? So thank you very much.
Thank you so much. Yes, and I know you're all hungry, so we're also going to change the schedule a little bit. So we have one more speaker now, and then we go to lunch, and then we move Peter Todd to after lunch. Next up is Gun. You saw him before at the panel. Come up, Gun. He is a professor at Cornell, a very bespoke gentleman, and almost 18 years into this field. So I don't think anybody else has that much knowledge about this. So go ahead and share everything that you know with us in 20 minutes. That's your goal.
Great. Thank you very much. I want to talk to you today about decentralization in Bitcoin and Ethereum. Oh, there we go. So you all understand, of course, that the main thing that brings people to cryptocurrencies, the main thing that renders them different from Satoshi coin as kept track of by a single person named Satoshi, is the fact that there is no single central entity, that these systems provide this elusive yet critical quality called decentralization. There's no single point of failure. This is, of course, crucial to their value proposition, and it's of course very, very important to their value proposition in general. So the fact that Bitcoin has been able to go for so many years, about 9 years in total, without a single moment of downtime, in comparison to systems like Amazon's, AWS, is a testament to the importance of this particular property. So the question here now is, well, okay, this decentralization issue, it's so important. Well, it's time to quantify it. Just how decentralized are these systems? Okay? And the decentralization goal has been used to justify lots and lots of decisions. We should go down this particular route. We should adopt these particular parameters for our protocol because they will aid in decentralization. Or if you don't do this, then the specter of centralization rears its ugly head. It's all going to belong to the Chinese miners if you do X, Y, Z. Well, to evaluate these, we have to get a handle on centralization itself. And to do that, we ended up 9 years in. This was a surprise to us that nobody had actually scientifically examined the issue of decentralization before us. But we did a rather large longitudinal study of decentralization on two very public, very well-known blockchains, on Bitcoin and Ethereum. And we did this with the aid of network and blockchain level data. Our data comes from 3 sources. We did a number of direct measurements. We went to every single public node on both of these networks that we could connect to, and we probed them and probed them and probed them periodically over a course of multiple years. We also looked at the blockchain state, and we also even went to the trouble of building a large network that attracted miners so that we could get our hands into the middle of the network and start observing things like orphan blocks and so forth that are difficult to observe from the edges of the network. And I want to report to you what we found. This is a very long study, lots and lots of data. And I'll skip this. And it's the critical questions then with all this data. There are 5 of them that we ask. The first one is, well, what are the resources available to the network? This question determines exactly how you pick parameters. If I'm designing for a bunch of small iWatch-like devices in the middle of the Sahara with almost no bandwidth, well, I'm going to have to pick certain parameters. Whereas if I'm building for data centers, it's a different world. And which one am I in? I don't really know. I don't think the developers know themselves. And so it's time to measure these things. Second is the decentralization issue. How widely are these nodes distributed? So they make a big song and dance about being distributed. Are they? How well decentralized are they? How about mining power? How is that distributed? And how effectively are we taking advantage of that mining power? And final question, what are the dynamics like? Are there forces in the system that cause people to coalesce? Because if that is true, then it's actually a dangerous slippery slope if people have an incentive to combine forces. I want to answer these questions very quickly. So let's see, what is available bandwidth? The very first question is, how much resources do these nodes have? And the critical resource here being bandwidth. So this limits the main bottleneck resource, and it's a very, very critical player in determining the block size used for Nakamoto consensus. What we did was we connected to every single node out there on Bitcoin and Ethereum that we could connect to, and we requested to download blocks from each and every one of them. And we divided the time into small epochs. We measured how much data we got in any one epoch. And we then picked contiguous epochs that spanned half a second and looked at the peak measurement in that half-second interval. That is to say, we went to a great set of lengths to measure the actual peak bandwidth ever observed from a node. So that gives us a good idea of what this node is capable of on a good day, on the best day we could possibly observe them. So that would hopefully correspond as well as it can to what this node is actually provisioned with. And the results look like this. So this is a CDF. The x-axis is bandwidth. The y-axis is the percent of nodes that have that bandwidth. So if you are to the right, life is good and you have more resources available. Just to orient yourselves, the green line is the set of Tor nodes on Bitcoin. So you can see that they're very, very under-provisioned. So if you're connecting to Bitcoin over Tor, you're looking at about 5 to 10 megabits per second. So, and you can see some other things like IPv6 nodes, the yellow line, they tend to be better provisioned than IPv4 nodes. Most interestingly, I think from this particular picture, we see that Ethereum is to the left of Bitcoin. So Ethereum nodes are actually less provisioned. They have less bandwidth available to them than Bitcoin. This is curious and interesting because Ethereum is driving its blockchain at a rate at least twice that of Bitcoin. So they have picked far more aggressive parameters, and yet they have less resources, and yet they're able to operate at that level. That's interesting. Another interesting fact, a result of our longitudinal study, is how this graph changed over time. And one line I'd like to draw your attention to is the median bandwidth available to a node, a Bitcoin node, in 2016 was 33 megabits per second. And so if you were happy with the amount of decentralization in Bitcoin in 2016, when the block size debate was raging, then by 2017, that number had gone up to 56 megabits per second. So your nodes got an improvement of 1.7x. Just as you sat there debating how to change things, the network improved by a factor of 1.7x. So you can actually improve or change your bandwidth parameters, your consumption of bandwidth, by a factor of corresponding 1.7x with no loss of decentralization. I want to now focus on latency because that also gives us an interesting insight into what's happening. So what we did was we looked at the network from various different vantage points around the world, from 18 different locations, and we measured the latency to nodes 1 and 2. What we want to understand, of course, is the latency between node 1 and node 2. This is a very elusive number, hard to get at, because you can't just ask somebody to please ping the person next to you and report me the result. They don't want to do that. So what we did is we pinged them individually, and so you want to get at this elusive number, but you can use the triangle inequality to get at this because you have some bounds of where this node could be. It could be as far away as that location or as close to that other node as that location. So that gives you, is it there? Is it there? We don't know, but it gives you that feasible region. So that establishes some bounds for the location of this node. Well, we did this from 18 different locations, so that gave us 18 different bounds. And if you combine them, then that gives you the feasible estimate of how far these nodes could be. And then we take the midpoint and report that. Okay? So this is sort of our best attempt at trying to characterize the internode distances on the Bitcoin and Ethereum networks. So now some of you might say, hey, on the internet, I heard that the triangle inequality does not hold. Yes, you're right. It doesn't always hold. There's no reason why it should always hold. But the number of times, the frequency with which it's violated is actually very, very rare. Okay? So here's what we see. There are lots of interesting things to take away from this graph, but one of the main interesting things is Ethereum is generally to the right of Bitcoin, so the nodes in Ethereum in the latency space are further away from each other. So these nodes are either more geographically distributed, or the networks that they're on are sort of in the network space farther away from each other. Bitcoin nodes tend to be far better, sort of far closer to each other in the latency space. What's the peak at the right? I don't know. Probably this probably corresponds to geographic distances. So there might be a bunch of nodes in China, a bunch of nodes in Europe, and a bunch of nodes in the US. But it's, I'm conjecturing right now, so and I don't know that for a fact. But you would expect to see the oceans in this graph. Right? So let's see. One interesting takeaway from this graph is 56% of Bitcoin nodes are in data centers. So there are all these people going around saying, oh, it's the cypherpunk reality, da-da-da-da-da. Well, you're building for data centers, okay? So that cypherpunk reality is something that exists in your mind. In contrast, in Ethereum, only 28% of nodes are located in data centers. That was a curious finding. So, okay, mining power distribution, we can quickly look at this. What we did is we looked at the blockchain, and we looked at each ranked miner here. You can see this is miner rank. And this is the amount of blocks that these miners got into the blockchain over time. So this is the CDF plot of the same thing. What are the takeaways here? I think the main takeaway is 51% of the mining power in Bitcoin is owned by 4 miners. For Ethereum, that number is 3. Okay, so if you want to do a 51% takeover, this is the number of phone calls you have to make. 90% of the mining power is 16 for Bitcoin, 11 for Ethereum. So if one could devise a Byzantine quorum protocol with 20 players, then you would already be more decentralized than both of these systems. And that's an interesting finding. Now, the problem, of course, is we don't actually have good, fair, open Byzantine quorum protocols that actually are capable of achieving this. So this is the motivation for all of the work that you see behind proof-of-stake protocols that are trying to essentially get at this particular state. And that would end up being not only more decentralized, but also greener as well. You'd end up consuming less energy. So one final thing I want to focus on is mining power utilization. So how much of the power that miners spent went into the blockchain? And so here we look at pruned blocks, also known as orphans, and we look at uncle blocks for Ethereum. And so we see a couple of things. This is mining power utilization in Bitcoin. This is the same for Ethereum. You can see interesting things. This is around the time of the DAO hack, and there was some instability and so forth, lots and lots of changes and orphans and so forth happening. But maybe the main important thing that I want to harp on over here is the fact that mining power utilization in Ethereum is lower, substantially lower, than Bitcoin. And Ethereum seems to suffer from lack of connectivity between its miners. It needs some kind of a better technology for connecting the miners together to each other so that there are less uncle blocks, which don't help with the serialization of the blockchain. So, okay. So, okay, actually, I lied. There's one other issue that I want to touch, which is fairness. So this was just absolute mining power. I want to look at the fairness among miners. And we came up with a metric, which is simply the ratio of blocks that are on the main chain versus the ratio of blocks mined by that miner. Okay? So you would ideally like to, for every block you find, you want that block to be on the main blockchain. Okay? You get rewards that way, and it helps the blockchain. To the extent that you fail to do so, it's bad. And so the question then is, what's fairness like? And is it better if you're big? Is it worse if you're small? Vice versa, what's the situation? So fairness of 1 would be ideal. And you see Bitcoin around 1. And here you see Ethereum. You can see that certain... this is Ethereum. Ethereum is around 1, I apologize. This is Bitcoin. You can see that certain Bitcoin pools were very well connected during the course of our study. It seems like Bitfury has a connectivity problem. It's actually suffering and losing a bunch of orphans. But overall, it's actually not so bad. What is actually worse here is the variance. So if you're a small miner with 1% mining power, you end up seeing all kinds of changes on a day-to-day basis if you're on Bitcoin. Ethereum, with its more frequent block size, suffers from less variance of block rewards. So, okay. So let's see, if I have, you're standing in front of, okay, I have a few more minutes, and I want to ask the final question. So what now? Okay, so we've learned quite a bit about decentralization. And so this elusive unicorn, it's very hard to find, right? It's, what can we do? So the first question, or first answer, or first big takeaway from this talk, if you take away none of the quantitative results, should be the following. If you're chasing unicorns, if you're chasing the unicorn, you should at least have some measure of progress. Okay? You should know what you're going after. You should measure it. Now, where is this thing? And you should keep in mind that perhaps the unicorns don't exist. This decentralization dream that's being sold may not be that easy to achieve. There might be inherent processes at work, such as availability of miners, people capable of building miners, and so forth, that actually make it substantially difficult for there to be lots and lots of different decentralized entities competing on the marketplace. Or the control over the code base might cause centralization worries. So what can one do? Are there other things that one can do here? And I want to switch gears and tell you a little bit about a project that was coupled with exactly this measurement study. We understand we need to scale. We understand that every new cryptocurrency out there needs to scale. We understand that every blockchain out there needs to scale. And where do we understand this from? Well, we see Bitcoin with its 3 to 4 transactions per second. So what is that? That's, to me, it's a crowded IKEA on a weekend. It seems like it's doing a few transactions per second. And that is not a sufficient basis to take over the world with. Ethereum is a little better. It's about at least twice, maybe 3 times better than Bitcoin in terms of throughput. But still, that's nowhere near enough to compete with Visa at 2,000 transactions per second. And if you want to achieve things like, you actually want to take over all gas station payments. That's about 400 to 500 transactions per second. You want to take over all vending machines. That's 1,000 transactions per second. You want to build a blockchain Facebook. Okay, so there are all these people who want to do decentralized XYZ. If the X there is Facebook, you have to handle 100,000 transactions per second. These technologies will not get you there. So I think one exciting option is to examine technologies that are centralized but untrusted. Okay, decentralization is a way to get at this lack of trust that's important, but it's not the only way to get there. It's possible to build systems that provide strong guarantees that they will live up to their specification, that they will do what they're programmed to do and nothing else, without having to have many copies of that system checking on each other. So one such technique that you have heard about today is trusted computing, attestation, Intel's SGX, and so forth. That's not the path we're going down on. The other one that's exciting, to me at least, is verifiably correct operation. So let me tell you a little bit about this Bloxroute project. What we're building is a high-performance network for disseminating financial data. So if you're in the business of building blockchains, then I think you're in the business, whether you realize it or not, of building a high-speed network. Okay? And that's not an easy thing to do. Everybody has been working at the consensus layer, where the problems are easier, nicer, cleaner, and a lot of people have ignored the network layer. So we're actually at the network layer. So what we're building is a pub-sub network, publish-subscribe network. We want to disseminate transactions to people who want to mine them. We want to take blocks and want to disseminate those to people who want the blockchain. So from the people who generate the data to those who consume it. It's a centralized network, but it's untrusted. You don't have to trust that it works, okay? And there are lots and lots of things for you to find out when it fails to obey the specification and to take remedial action around it. So I want to tell you what makes it so fast. And I want to tell you exactly what most people do. If you are building any kind of a blockchain thing, you're probably doing this. You have a source that has a block, and that's the block that's about to be transmitted. It takes some time beta. Somebody receives it. They first process it. They check to see if it's a good block, and then they send it on. Okay, so that's this verification time alpha. And so then this peer receives that block at this point in time down here. This is a timeline going down. So that's fine. and that's the source of your latency. So if you have n such people, then you have a latency that is n, number of relays in the middle, times this verification latency plus the block transmission latency. That's n times alpha plus beta. So I'll just, here we go. I don't know why this suddenly, okay, here we go. We're going a little faster now. It's PowerPoint. Okay. So I want to tell you a little bit about why what we're doing is different. When we receive a packet, we do this thing called cut-through routing. We immediately send it to its recipient. And in doing so, we keep attribution information such that when the ultimate recipient receives it, and if there's a problem with the data, they know to blame the source and not the relay. And this fast relay network then takes time alpha prime, much, much less, to send the data on. And if you look at the overall complexity of this operation for n relays, it is not n times alpha plus beta, it's n alpha plus beta. So we got rid of the n beta factor, and that is a crucial factor in speeding this up, because beta is typically large, and getting rid of that linear factor is essential in speeding this up. So that's the system that we've built. It operates. It's already in existence. This is there's now a company that's funded and a group of 5 people working on this at the moment. We're very, very young. Just happened about a week ago. But the system is real and it operates. It's operating. It relays these transactions and blocks. And think of this company essentially as the infrastructure company for all other coins. We do the dirty work that most cryptocurrency implementers either don't want to do or don't do very well, at least at the moment. So the crucial aspect of the system is that it's provably neutral. So it guarantees to you that it will not preferentially treat any of its clients. That is, every client will get the same treatment, and it will be fair. And if it ever misbehaves, you know, and you have cryptographic proof in your hand of misbehavior. So I want to conclude by saying that decentralization is a wonderful thing. It turns out that two big cryptocurrencies that we looked at are not very decentralized. And it's very elusive. It's hard to get that decentralization. And so we need better mechanisms for building systems that operate without trust, that are not necessarily decentralized, but at least untrusted. And maybe my final word here is a good workhorse beats a non-existent unicorn any day. Okay, thank you.
So
lunch.
Yeah, we have lunch. Did you raise money for the?
Yes, we got some funding.
Yeah, funding. You don't need anything else. I have $10. Put it.
Okay.
Okay, we're gonna have lunch. We're gonna be back. Let's see, at 5. So what is that? 3:25. So it's got to be a quick lunch, and then we're gonna have Peter talk.